asking for that, because I forget a lot, and I appreciate your help in keeping that straight. All right, so any other questions about the test? Sort of functional questions? Are we ready to do review then? Awesome. So I want to tell you that though we are separate, though it's a weird day because we're on Zoom, we are here to learn. So who has a question? Carrie, yeah, go ahead. Carrie, I think you're muted.
Sorry.
You're good.
Could we start with number 3 on the 7.1 homework?
Absolutely. So I'm going to pull that up. It's going to take me just a moment, and then I'll pull it up. So 7.1, number 3, yeah?
Mm-hmm.
Okay. Let us share screen. I don't know of a way to, well, it doesn't matter. I'll just share it anyway. Can you guys see my screen? Yeah. So this is the vector space, and the question is which properties are satisfied and which are not. So you can see according to the answer key which ones are satisfied. Here we have a weird addition. This one right here is the addition A1B1 plus A2B2. It gives a 0 up here, and then the second addition is as a normal, and scalar multiplication looks the way it ought to. So did you want to look at all of those, Carrie, or some in particular? We can go through all of them. It's up to you.
Yeah, I kind of just wanted to see it like step by step, I guess.
Let's see.
I mean, I get, so property 1 and 2, it's just because like they've given us the addition and scalar multiplication and it looks fine.
Right. So let's see. Right. So for property 1 and 2, you have to check closure. So basically in this thing, it's just ordered pairs. So the big question is, if I add 2 ordered pairs together, do I get an ordered pair? Yes. And if I take an ordered pair and I multiply it by a number, do I get an ordered pair? Yes, right? There's no special property for, there's no special really condition for membership other than being an ordered pair or, a two-dimensional vector. So 1 and 2 are good. Does it say 1 is not satisfied? That seems weird.
No, the key, like the green key is next to it.
Oh, yeah, sorry. So property 1 is satisfied. Yeah, you're right. Property 2 is also satisfied. Property 3 says that there's a 0 vector. So let's take a look at that one. Give me just a moment to sort of share my other screen. Let's see. Maybe. Nope. I always have to figure out how to do, there we go. All right. I'm going to have to stop sharing this screen so I can share my other screen, but I'll sort of walk us through what is needed here. Hopefully. All right, so you guys can see this, yeah? Hopefully. Nope, it says nothing, right? Do you guys see? You guys don't see anything. That's lovely. Let's try again. All right, try one more time. I blame COVID. Should be better this time. Do you guys see just a blank black screen?
Yeah, just a blank black screen.
That's very weird. Do you guys see like a blue screen now?
Yeah, we see notability.
Got it.
we see a white screen.
Better
but
now, yeah? Thank you, guys. All right, and I'm going to see if I can make sure. I can't see everybody at the same time. That's okay. There we go. Okay, so there's a 0 vector. So I'm going to say what it is up here. Again, this is what I'm going to write it a different way just because I don't want to write all those things. This is 0 and b plus d. I'm going to change this a bit so it's not as big so I can actually write. So this is the definition of the addition. And the big question for property 3 is there a 0 vector? So, you know, is there a vector so that when you add it to something else, it remains unchanged? I mean, here, you know, basically, can I choose CD so that this result is AB, right? So that's sort of the big question here, right? If my CD were my 0 vector, if I'm thinking about my CD as a possible 0 vector, the way to make that work is for the answer, the result to be A comma B, right? But you can see if I choose D is equal to 0, you know, D is equal to 0 would be a good start, because if D is equal to 0, then that bottom, then this guy here, then this guy here is going to be what I want it to be. But there's no choice of A that makes this guy work. Does everybody make sense? Cannot choose C to make this A, right? There's no 0 vector. Does that make sense? So any questions about that one? Okay. So let's see. Right, and if there's no 0 vector, I mean, the next one says there's an additive inverse. Well, if there's no 0 vector, then it doesn't even make sense to ask if there's an additive inverse, right? Because it's not possible to add two things together to get a 0 vector because there is no 0 vector. Does that make sense? So really, I mean, property 4 sort of relies on property 3. So if property 3 is not satisfied, property 4 cannot be satisfied. Does that make sense?
Why couldn't, if D was just, oh, it's the inverse. It's the inverse. Never mind.
You good? Other questions?
Actually, no, I do have a question.
Yeah, go ahead.
So say like A and B were like 2 and 3, and then C and D was -2 and -3.
Mhm.
Is that the additive inverse?
No, because when it says the 0 vector, it means whatever thing that you found in property 3.
Oh.
The 0 vector here is not the one necessarily that has 0,
right.
0, right? It's some weird thing, you know, it could be something different or weird. You know, since there is no 0 vector, like I can't find something so that V plus negative V is equal to 0. The 0 doesn't exist. Do you know what I'm saying?
Okay.
Yeah. So I might say, you know, can I make this happen? No, this doesn't exist. Bless you. All right, so far so good. Those are good questions. We ready for 5? Okay, cool. So property 5 says all these different things. So let's see. I mean, it looks like property 5 are all satisfied. I think maybe it makes sense to do 1 or 2 of these. We'll do a couple and then we'll see how people feel, okay? So let's do the first one. For all V1 and V2, that addition is commutative, right? So I got to check V1 plus V2 is equal to V2 plus V1, right? So if I'm doing this, I might think about this as my AB. I might think about this as my CD, right? I'm going to name those vectors. And the big question is, if I add them like this, does it matter? Does it matter which order I add them in, right? And so usually to do property 5, I want to compute the left-hand side, like this is my left-hand side. and I want to compute my right-hand side, and I want to compute them separately, and then I just want to sort of compare at the end whether they're always the same. Does that make sense? So, so I'm going to go back to my definition for the left-hand side. The definition of the left-hand side is this is equal to 0 and b plus d. Okay. And over here, if I look at my definition, right, again, it's definitely 0 up here. But now I'm adding, you know, I'm adding this thing plus this thing. So I get d plus b. And the question for us is, are these two things equal to one another? Is 0 b plus d equal to 0 d plus b? Yeah, right. I mean, I know that when I add two numbers, it doesn't matter about the order in which I add them, right? So this one is satisfied. This is property 5a. Yeah. Does that make sense?
Mhm.
Okay. Carrie, do you want to go through all of those, or there are some that you wanted to look at in particular?
No, I think I'm good on those.
Okay, cool. Does anybody else want to see any of these? I'm happy to go over one or two more. Again, please speak up. We're all here to learn. If you've got a question, I'm sure somebody else got a question too. Laura, you want to see one?
Can we go over why 5D isn't one?
Yes. It's why 5D is not. Yeah. So you're right. I missed the fact that 5D is not. Absolutely. That's a great question. Laura, was that your question too? Awesome. See, I told you guys, if one person has a question, probably other people do too. For all V1 in V and real scalars C1 and C2, we have this. C1 plus C2 times V1 is equal to C1 V1 plus C2 V2. All right, so we want to really check this property. 5D. C1. Yeah, okay. So here I'm going to let I'm going to let this guy be AB, and I'm going to let this be just C1 plus C2. That's fine. And over here, I'm looking at C1 AB plus C2 AB, like this. I'm not going to write that they're equal yet because I don't know that, right? So one of the things that we talk about when we do problems like this is I shouldn't be as certain something is true until I've checked it, right? So let's think about the definition. Right here, the definition is I just take whatever this number is. I take this number and I use the definition of scalar multiplication to see what this is. So I believe that the definition of scalar multiplication is this. Right, it's sort of normal. I just take that, you know, that scalar and I multiply it through as I normally would. Okay. On the right-hand side, it says to first, you know, multiply by C1, first multiply by C2, and then add them. So I'm going to do that maybe in 2 steps. Here's my first step. All right, so here's my first step is when I just use the definition of scalar multiplication to sort of take that in. And then now I'm being asked to add these two vectors together. So I need to use the definition of addition. All right, so these two are equal, these two are equal. So let's use the definition of addition. Remember, addition says to, when I combine things, put a 0 in the first spot and then add the second spot as normal. And the big question is this thing here, let's make that one, you know, is this thing here always equal to this thing right here? Are the two highlighted things equal? They are not equal, right? I mean, sometimes they are, but they're not, they don't always have to be, right? So 5D not satisfied. Does that make sense?
Yep.
Awesome. Good. This is a good question. All right. So other questions about this one, about number 3. Any others that you want to see? All right. Very nice. Who has a different question? I'll put that back up here so you guys can, if you guys need that. Laura, yes.
I had a question about the 7.2.3 homework.
Gotcha.
Well, I had a lot of questions about it, but could we do number 17 just to start off with?
17 to start off with, yes. Gotcha. This is about determine whether these polynomials is a basis for P2. Okay, perfect. I'm going to first share my screen. Gosh, there's so many buttons. I think this one. All right. Can you guys see just the question without any scores in the background? Okay, you can't. Okay, good. So I'm not committing FERPA. That's good. I'm not committing FERPA right now. I'm not actively committing FERPA. Okay, so this is the question. Determine if the set V is a basis for V. Gosh, that always annoys me when they choose the same letter so that when you say it out loud, it doesn't really, you know what I mean? But so let's see, I'm going to write these down. X squared minus 3x, and then I'll share my other screen. Plus 6, 3x squared minus 5x plus 8, and x squared minus x plus 1. And I'm looking at sort of P2. Okay, so determine if it's a basis. Okay, so I'm going to stop sharing this screen. And I'll share my other screen. Doggone it, it's doing this weird thing again. That's okay. Let's try again. You guys see that? Okay. Awesome. So yeah, so in order to understand whether it's a basis or not, I need to know whether these are linearly independent and whether they span. Okay. So maybe the first question that I've got in my head is, what do I think the dimension of P2 is? Just as a guess. I mean, what do I think the dimension of P2 is? How many degrees of freedom do we have in P2? 3, yeah. Because they're basically, you know, P2 consists of quadratic polynomials, degree 2 polynomials. So I've got my coefficient for my degree 2 term, my coefficient for my degree 1 term, and my constant term. So that's definitely 3-dimensional. So it's certainly possible for this to be a basis since there's 3 things in there, right? I should expect that any basis has 3 items in it. The question is this a particular, you know what I mean? Does this one work, right? So, you know, I'm going to check that first, because if I can if there are only 2 items, I would know immediately there's not enough, and I could just say on my test there is not enough, right? I mean, I could very much say that and save a lot of work. Here I'm going to have to go through it. So let's think about whether these are linearly independent and whether they span. So linearly independent, and do they span? Okay. So maybe the easiest thing to think about is whether they're linearly independent. So let's think about that first. So I'm going to think about whether they're linearly independent first. In order to know whether they're linearly independent, I look at C1 times my first vector plus C2 times my second vector plus C3 times my third vector and I'm going to set that equal to the 0 vector. Let's not write it that way. Let's be careful. The 0 vector here is the 0 polynomial. I'll just write the 0 polynomial as the one that's identically 0, and we'll sort of know that that means the one that's 0x squared plus 0x plus 0, right? All right, that's sort of what we're keeping in our head. And then once I have this set up, what should I do next? What might be a good next step to sort of switch things around?
Regroup them based on x squared, x, and constants.
Perfect. So let's do our x squared stuffs first. So I'm going to regroup. So let's see. So here I've got a C1 maybe plus 3C2 plus C3. That's all my x squared stuff when I sort of multiply out and sort of group. Let's think about my x stuff. So my x stuff is that. Again, check me to make sure I'm doing this right, because I screw this up all the time. It's really easy for me to screw this up. And my constant stuff. All right, and I'm going to scroll up just a little bit. Okay. All right, so now that I know this, what can I do next?
Write it as a system of equations.
Cool. So I'm going to equate coefficients, right? So if I equate coefficients, that's the same thing as getting a system of equations, right? Sort of with the understanding that all the coefficients on the right-hand side are 0. So let's see. Here's my first equation. C1 plus 3C2 plus C3 is equal to 0. Minus 3C1 minus 5C2 minus C3 is equal to 0. 6C1 plus 8C2 plus C3 is equal to 0. Right? Just by taking each one of those coefficients, you know, my coefficient for x squared, my coefficient for x, my coefficient for my constant coefficient. Then I probably just want to solve, right? Now I don't have a calculator handy. I will say that I happen to know that if I do, oops, let's do this one right here. If I do reduced row echelon form of my augmented matrix, sorry, for linear independence here, what am I looking for? What's my goal for linear independence? What do I want to know?
You don't want any free variables or free
Good.
variables.
So I'm looking for free variables, right? So if they're free variables, that means that there are non-trivial solutions, and that means that it is linearly dependent. So I'm looking for free variables. I will say there are free variables. My guess is just one. There is a free variable here. So this means that there are non-trivial solutions. Which means that these are linearly dependent. Okay. Does that make sense? So any questions about that one?
I have a more general question. My first question is, how come sometimes we use P instead of R? Like, it seems like they're used in the same type of scenarios, but are they different?
P instead of, you mean like the P2?
Yes.
Yeah, so P2 just means polynomials. P stands for polynomial.
Oh,
Yeah.
what does R, is R the,
So Rn stands for Euclidean space. So it means columns of vectors.
okay. And my other question was, what were you saying about like the dimension and the degrees of freedom, like what the rule is for that? I don't quite remember that.
Yeah, so if let's see, I know that the dimension of P2 is equal to 3 since there are 3 degrees of freedom. I mean, in general, there is a theorem in your book that says exactly what the dimension of these spaces are. I'm thinking this is so let's change my, I'm going to change my font so that you don't, this is sort of my thinking. This is my thinking. I don't write this maybe down. A0 plus A1x plus A2x squared, right? When I think this way, I'm thinking of 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom, right? So a degree 2 polynomial sort of has 3 different spots that can sort of be whatever they want to. So if, nope. Let's go back to my blue. So if I'm considering 4 vectors, they cannot form a basis. Right, there are too many vectors there. I chose 4 just randomly, right? If somebody gave me 2 vectors, I know that that would not be enough vectors, right? The right number of vectors to form a basis for P2 is 3. And if I'm given any number other than 3, then I can automatically dismiss it. I know for a fact that it cannot possibly be a basis, right? Because every basis has the same number of vectors. And so since I already sort of at the beginning know that the dimension of this space is 3, then I know that 2 is not going to be enough. I know that 4 is going to be too many. I mean, basically, you know, I know that this is a 3-dimensional space. It's like 3-dimensional space. And if I said to you, here are 2 vectors for your drone, can the drone get everywhere? No, your drone needs at least 3. And if I gave your drone 5 vectors and said, does that sound good to you? You'd say, no, I know that 3 vectors is the right number for my drone to get everywhere and not have extras. Does that make sense, Gary?
Thank you.
Sure. Laura, so just to make sure, to close the loop on this one, linear dependence means that these vectors cannot form a basis. Yeah. Because in order to be a basis, they have to be linearly independent and also span. I will say that, you know, generally what you're looking for is a pivot in each row and column. If you don't get a pivot in every row and column, you know that there's a problem, right? So if there's not, so I'll just sort of maybe, again, this is me thinking, so I'm going to do it in my pink. Apparently I think in pink. You see what I did there? It kind of rhymes. So here's my thinking. You guys, that's hilarious. It's hilarious. It must be really early if you're not laughing at that. To be a basis, I'm really looking for a pivot in each row. If I get a pivot in each row, I know that that has to do with span, okay? And a pivot in each column. That's linear independence, right? So for a matrix that you arrive at, right? Again, I put this in pink because I sort of have to, memorizing that is good, and that will be very, very good for a test, but sort of being able to trace through the reasoning there is important too. So notice up here, when I said, when I'm looking at the, in this part, when I'm looking at the reduced row echelon form of the augmented matrix, I look to see if there's a pivot in every column. I didn't sort of say that, but there's not. That's sort of the thing that I'm looking for linear independence. Since there's not a pivot in every column there's not a pivot in every column. That means that there is free variables. That means that there are non-trivial solutions, and that means that it's linearly independent. So what I'm saying is, this is the sort of thing that I should write on a test to communicate that I understand those connections, right? Rather than just saying, oh, there's not a span in each column. That's good enough. I'm done now. The effect is that, but it's important to communicate these links. Does that make sense? So I want to make sure that that sort of that we sort of have those links in our brains. Laura, does that help? Is there any questions about that one? Cool.
Yeah, I think I'm good on that one. The book had said to do some like a method where you include x squared, x, and 1 in the whole set that you're using.
Yeah, so that is if you are trying to extend a basis.
Oh, okay.
So if you are starting with some vectors and you want to sort of extend the basis, then you do that. We did not get time to go over that, Laura, in class. We were going to, but we didn't. So I'm not testing on that.
Okay.
And I thought very seriously about sort of putting that on the next test, and I'm not going to do it. That feels not as important for what we're about to do. So we're not going to do that. And I should have made that clear in the reading, so I apologize. That's totally my fault.
I have a question about the spanning.
Sure, go ahead.
So for a pivot in each row,
Mhm.
is that if there's a 0 row, then that's okay unless it's like 0, 0, 0 is equal to like something 1 or B.
Yeah, so that's a great question. So how do I say? So usually when you're looking at a pivot in each row, you're looking at a non-augmented matrix. Does that make sense, Carrie?
Okay.
So if you're looking at a non-augmented matrix and you have a 0 row, once you augment that pivot, you're going to get zeros is equal to something. So that's my thinking.
So like when you're trying to find whether something has a basis or not, it is going to be augmented. So you have to check for that. But
It's
like
up-
on its own, if it's asking if something spans, then it's okay if it has a 0 row since it's not augmented. don't-
No, I mean, again, that 0 row is sort of always going to be an issue.
Can I
Let me say what I mean by that. Let's just suppose you're thinking about here's what we'll do. I will sort of go back and sort of look at the last one, thinking about it in terms of span instead of linear independence. Okay.
Could I show you one that
Yep.
is a good example? Number 11 on that same homework.
Number 11 on the same homework.
It
Absolutely.
asks whether something spans but is not linearly independent.
Gotcha. Number 11.
0 rows.
Yeah, I mean, so I can show that one. This one is nope, that one right there. Can you guys see just number 11 without anything else? Carrie, can you see just number 11?
Yes.
Okay, cool. Yeah, so this one, I would think about this one a little bit differently. It says a subset of R2 by 2 that spans R2 by 2, but is not linearly, independent. So if I know that it spans R2 by 2, I know that it has to have enough vectors to get everywhere. How many vectors are in a basis for R2 by 2? What is the number of degrees of freedom? It's got to be 4, right? So because a 2 by 2 matrix has 4 entries in it. You know what I mean? Like the top two, the first row has 2 entries. The second row has 2 entries. We know that the dimension of R2 by 2 is 4. So in order to span R2 by 2, I need at least 4 vectors to get everywhere, okay? In order to be not linearly independent, it needs to have something extra, right? So really, there's only 2 possibilities for that, right? There's the second possibility and the last possibility, okay? I see what you mean. So let's see. Oh, yeah. So if I look at this one, yeah, let's look at this. I'm writing it down now. Okay, so let's look at this one first to see whether we think that this one spans and is linearly independent. Sorry, but is not linearly independent. Sorry, not linearly independent. So this is like number, I should write this one down. This is like number, oh, I don't know. Which one did we say this one was? Number 11?
Yes.
Number 11 on 7.2, 7.3 homework. Okay, so I'm gonna stop sharing and share my other thing. It's gonna be weird again. What do we want to bet? Let's see. Oh no, it's weird. Look at that. But now I got your number notability. Ha. So this is the one that we're looking at, and we sort of want to know whether this spans and is linearly independent. So I'm gonna say we want to know really whether it spans or not, right? So spans.
Is that last one all ones?
No, that's a good question. This one is a 0. I'll fix it. Sorry.
Right.
And this one is also a 0. All right. So spans. So really here I'm looking for something like this. I'm looking for C1 V1 plus C2 V2 plus C4 V4. Whoops. Right. In order to span, I want to know whether this has a solution. That's not a 0 or an O. Solution for all B. That's sort of the question. So let's sort of, oh, I'm gonna have to need that right there. So I'll write it this way: C1 1 0 0 0 plus C2 0 1 0 0 plus C3 0 0 1 0. Oh, and it's 5. I should have done 5. My bad. Let's call it WXYZ. Okay, so that's sort of my very general sort of vector. And the real question is, does this always have a solution, right? Is there a solution no matter what W, X, Y, and Z are? So I might sort of, I hesitate to do that. That's okay. C1 0 0 0 0 C2 0 0 0 0 C3 0 0 C4 C4 0 C5 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 0. Right, like so. So here I just multiplied I just multiplied by my scalars. Okay, so let's combine all that. So I'm just going to add all the stuff on the left-hand side. So let's see, all the stuff on the left-hand side. In that top left entry, I see one C1 and one C5. The next entry is a C2 plus C4 plus C5. Bottom left is C3 plus C4 plus C5. And bottom right, what do you see in the bottom right?
0.
That's what, yeah. And that's the key.
Okay. I think I was thinking you could just look at them and tell. And I think all the other ones right. So I'm glad that I asked about this because I was doing it wrong.
Yeah. Well, I mean, I was going to say you could, like, if I had looked at this one carefully and noticed that there was nothing going on in that last sort of entry, then yes, you could sort of immediately say that they don't span, right? There's no way to get a 5 using those vectors as linear combinations in the lower right-hand corner. Does that make sense, Carrie?
But can you necessarily see linear independence by looking at it?
Sometimes, sure. So what I look for linear independence is sometimes you can, sometimes you can't. When I look for linear independence, I sort of look, is there sort of an obvious way to add 2 of the vectors together to get a third vector? Because that would tell me that they are not linearly independent, right? That they are linearly dependent. And sometimes you can tell that. Sometimes, it's too hard to tell. So you have to sort of go through the whole process.
What do you mean, like add them to get a third vector?
Let's see. I'm trying to think. In this example, notice that notice that if I take the first vector, 1 0 0 0, if I take the first vector and the next to last vector, 0 1 1 0. And I add those 2 together. Notice I get 1 1 1 0. Did I do that right? So this is the first vector. This is vector number 1. This is vector number 4, and this is vector number 5. So the fifth vector in that set is the sum of the first vector and the fourth vector. And that means it can't be linearly independent, right? I mean, we know that that is a linear dependence relationship. So, you know, sometimes it's easy, but sometimes they're written in a way that it's sort of hard to tell by inspection. Carrie, does that make sense?
Yes, sir. Thank you.
But that would be the thing that I've just written down, right? This is sufficient to show linear dependence, right? That's a linear dependence relation. That means that there's certainly non-trivial solutions to the thing, right? You know, you can sort of rewrite this to find a non-trivial solution to the homogeneous equation. So Carrie, I don't know if I answered your question. Did I answer your question?
Yes, that did. Thank
Okay,
you.
cool. I'm just gonna just sort of really quickly, just sort of very quickly sort of say what this is gonna look like. If I write these down as equations, I get this one, I get this one, I get C4 plus C0 plus C4 plus C5 is equal to 0, and I get 0 is equal to 0. And so nope, I do not get that at all. Let's try again. This last column I screwed up. Let's see, I get W, X, Y, and Z. So when I do my augmented matrix is going to look like this. 1, something, 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 right? That's what my augmented matrix is going to look like. And I can already tell, oh, that's not what I meant to do. Let's try again. I can already tell from this last row that, you know, there's not a pivot in that row, right? Or the pivot, I can think of it in two ways. There's not a pivot in the non-augmented matrix in that last row, or the pivot in the augmented matrix is to the right of the augmented thing, right? So either of those ways of thinking, I think, is the right way to think about it, right? So let's say no pivot in last row of non-augmented matrix, or pivot in augmented matrix to right of bar. Those two things mean the same thing, right? Those two things mean exactly the same thing.
It doesn't span.
Yeah, right. So that's exactly say that it does not span. Exactly. So there are choices of B so that system has no solutions, which means they do not span, right? There's something that's going to go here. I'll highlight in a different color. You know, I can choose things here to make 0, 0, 0, 0, 1, right? And that is exactly what it means to that they do not span. It's inconsistent. There's not a solution. They don't span. All right. So any questions about this idea of spanning for these sorts of things from anybody else? All right, great. Somebody else who hasn't asked a question, lay one on me. Yes.
Can we do number 2 on the same homework assignment?
Sure. Allie, I'll get yours next, okay? Number 2 on the same homework assignment. We're asking, this is determine if V is in the subspace spanned by something. Is that right, Becca?
Yes.
Got it. All right. All right. So here we're given two vectors that span a subspace, and we're asked if this vector is in that span. So basically, you know, here are my two directions for my Roomba or my drone, and I'm given a third thing and saying, can my Roomba get there, right? So let's see, is v, which is 5x squared minus 10x plus 13 in span of, and then I'll share this as soon as I get it written down. This is number, we said this is number 3, Becca?
Number 2.
Sorry. And cool. All right, so this is my question, right? Is this particular vector, this polynomial, in the span of these two things? So when I think about span, remember that span is the set of all linear combinations. This is set of linear combos of the two vectors. So, you know, I'm asking, can I write this vector right here as linear combo of this, two different greens, that's okay. So my question is, can I write that vector as a linear combination of these two? So let's attempt to do so. Let's say 5x squared minus 10x plus 13. A linear combination is just some sort of way of combining those two vectors with different weights. So I'll say something like C1 times my first vector plus C2 times my second vector. Right. And the big question is, can I find C1 and C2? Right. Right. To make this work. So I'm going to do what I've done before, and that is sort of group things nicely and then equate coefficients. So let's see what that looks like. Let's see, I'm going to get my x squared stuff together first. I'm going to get my x squared, my x stuff together next, my linear terms. So I'm just going to group those things, right? So far, so good. And then I want to equate coefficients, right? So as an example, this thing and this thing have to be the same because they're both x squareds. And this thing and this thing, and I see I left something off. Let's fix that. Those two things have got to be the same because they're the same coefficients. And you know, likewise with the constant terms. So let's say 3c1 plus c2 is equal to 5. C1 minus 2c2 is equal to negative 10. And negative c1 plus 3c2 is equal to 13. Please check me to be sure I didn't make any mistakes. Does this all look right? Okay, cool. And again, I just want to know if there are solutions. So I'm going to look at the reduced row echelon form of I'm going to look at the reduced row echelon form to that. And I don't know what I'm going to get, but I'm going to get something that looks like, and some other stuff. Right, so I'm going to get something that looks like this. I probably get something that looks like the identity matrix up in the left-hand side. That's my guess. Is that right, Becca?
Yeah.
So I get 1 0 0 1, probably 0 0, right? I get, that's sort of what I get. This last thing says inconsistent, means no solution, and that no solution means you know, it's not possible to write our vector as linear combinations of given vectors. So my answer is no. Becca, does that make sense?
Yes, it does.
Cool. Any other questions about this one? Awesome. Allie, did you have a question?
Yeah, can we go over number 3 on the test?
Sorry, Allie, I couldn't hear you. Could you say it again?
Can we go over, I don't
Number 5? 3. Yes, sorry. Yes.
She said from the test review, by the way.
Oh, from the test review. Thank you. I missed that at all. Test 3. Yeah. Thank you, Carrie.
Welcome.
Number 3. Allie, is this about finding a basis for the column space?
No, it was,
Gotcha. Hold on. I got it.
okay.
Sometimes I randomize the order and sometimes I don't. So this time it was random. So number 3. Find all values of x so that, does that sound right, Allie? Okay, cool. Are you, yeah, I don't know how to do that. Allie, in order to show this, I'm going to have to reveal like yours. Are you okay with that? Okay. I mean, the scores doesn't really matter, right? And I will say that, yeah. So many people have not looked at this one at all. So, so you are ahead of many, many people. So again, number 3, find all values of that. Let's share my screen. All right, can everybody see that now? Okay, so number 3, find all values of x so that rank of A is equal to 2. So we want rank of A to be equal to 2. This is from test 3 review. All right, so I've got it written down, so I'm going to share my other screen. All right, so we want for the rank of A to be equal to 2. So when I think about rank of A, what is the definition of rank of A? Anybody?
The dimension of the column space or the row space.
Good. So it's the dimension of either the column space or the row space. Good. And Allie gave, I'm so proud. Allie, you gave the correct definition. So that's exactly right. What do we think about often when we think about rank? Sort of what's the natural way to sort of be able to look at a matrix and tell its rank? You know, dimension of column space, that seems kind of complicated. Dimension of row space, that seems kind of complicated. What's the right way to think about rank of A? It's the number of pivots. Okay, so rank of A is always the number of pivots, right? So the number of pivots is going to give me the dimension of my row space, and it's also going to give me the dimension of my column space. So, so let's see, dimension of row or column space. Good. Which is happens. This is the definition. This is the definition, which is equal to number of pivots. So again, that second part is not the definition, it is a consequence of the definition, okay? So really, we just want to start maybe doing row operations until we can guarantee that the rank, that this thing only has 2 pivots. So I'm going to start having to do row operations, I think. Unless does anybody see some sort of obvious thing that would make it so I don't have to do a whole bunch of, I don't see anything obvious. Okay, so I'm going to start doing row operations. I'm going to first sort of swap rows to put that last row in front because I like that 1 there. I'm going to leave that one there. And I'm going to add maybe a multiple of that row. Yeah, I'm going to say sort of take add 3 times bottom to top, right? And that's going to give me a 0 where I want it. Okay, so let's see. Do I get negative 15 maybe? Okay, so check me to be sure I did that right. When I do 3 times 1, I get 3. And when I add it to 2, I get 5. So I think that I got the right thing, hopefully. Does that look right? Okay. Okay, so I think I can do, there's one other row operation. Again, I want to sort of, I'm thinking about reduced row echelon form. So really, I would like to get a 0 in this position. Sorry, nope, missed it. I want to get a 0 in this position. So here I might sort of take minus row 2 and add it to row 3, and that'd be my new row 3. That 1 is going to cancel with the 1 there, which is what I want. Minus row 2. Yeah, okay, so minus row 2 is minus x plus row 3 minus 15. And when I do this one, I get a 0 here as well. Does this make sense so far, everybody? All right. So I think that that's probably far enough. I'm thinking about making sure that I only have 2 pivots. Notice that I have, here's a pivot. Here's a pivot. What do I want? I mean, what do I want here? If that thing is a pivot, then that's bad because that would mean that I have 3 pivots, not 2 pivots. Right. The only way to make just 2 pivots is to make that red highlighted thing 0. Need only 2 pivots. So need minus x minus 15 to be equal to 0. So, and I can solve that and I get x is equal to negative 15 by maybe adding x to both sides. Does that make sense? Any questions about it? Yeah, so that one I think I have to do row operations. Gosh, it's been a while since we had to do row operations, hadn't it? So it's good review for our final exam coming up. Cool. Thank you, Allie. That's a great question. So has someone got a different question that we'd like to look at? Laura, you've got a different question? Which one?
I believe it's
Is it from the review or somewhere different?
7.1 homework.
Gotcha.
Number 6.
Okay. Is it this one? Cool. So a vector space V and a subset S are given. Determine if S is a subspace of V by determining which conditions of the definition of a subspace are satisfied. Select all that apply. So this is a weird one. This is functions, basically functions that are continuous from -3 to 2. Not that I think that that's relevant for this problem, but that's just what the definition is, right? So that's what C -3, 2 means. Continuous functions on the interval from -3 to 2. S consists of functions of the form A times e to the bx. So A and B are real constants. So here the criterion for membership into our set is a little weird, okay? So I'm gonna maybe stop sharing and sort of think through this one. I'm gonna share it with the other screen, sorry. Okay, so, and which number was this, Laura?
Number 6.
Got it. So it's 7.1, number 6. So here we have, you know, my criterion for membership to my set must look like A e to the bx. It must have that form, right? So the first question I've got is, does S contain the 0 vector? So I need to think about what the 0 vector is in this case. So the 0 vector is a function, so that when I add it to another function, right, it doesn't change it, right? So here, the 0, yeah, so this is the first one. The 0 vector is the function f of x is equal to 0, right? The only way to take a function and add it to another function and have it be unchanged is if that the original function is identically 0 everywhere, right? That's the only way that that's going to work. So the real question is, can I write 0? You know, can I write 0 in the form A e to the bx, right? I have complete control over both A and B. So since I have control over A and B, what would be a smart choice for A here? I'm going to choose A is equal to 0, right? Then f of x is equal to 0 times e to the bx, but 0 times e to the bx is certainly 0, right? So all this is to say that the 0 function or the 0 vector meets the criterion for membership. So this one is okay. So far, so good. I'm going to do this one in a slightly different order. Sorry, did anybody need that? Is anybody still writing? I can scroll up. That's okay. Okay. I'm going to do closed under scalar multiplication next. So let's see. So start with f of x in S. So f of x has to look like this. Right, so I know that since f of x is in my set, I know that it has the right form. And the question is C times f also in S? Right, so C times f, the C, A, E to the BX. C a to the e to the bx, we just need to know, is it in the right form? Is it some number times e to something times x, right? So does this have the right form? Yes. It has, you know, number times e to the other number x. Do you know what I mean by that? That's sort of terrible writing, but I'm trying to communicate. It's just some number, even though that number is complicated, times e to some other number times x. So yes. Right. That's not a hashtag, by the way. That's the number, not a hashtag. I'm not tweeting. Now or ever. Okay, so so the final one is closed under addition. So here we will start with two functions, f of x and g of x, in S. And the big question is f of x plus g of x also in S. Right, so if the two functions start out as satisfying the criterion for membership, does the sum. So here, I'm thinking f of x has to look like a e to the bx, and I know that g of x looks like that as well. It's not the same a and b, so I'll change the letters. Let's say it is c e to the dx. Okay, it's just some number times e to the some other number x. So then, if I add those two together, the real question is, can I write result as something times e to the something x? There's no way to combine those two things. So I'm sort of stuck. Do you know what I mean? That's sort of maybe not a very satisfying answer, but like no. Cannot combine two exponentials, sum of two exponentials into a new exponential. Right? There's no algebra that's going to allow me to sort of combine them. There's nothing I can do. So this one is not satisfying. Does that make sense?
Yes, thank you.
Sure. Other questions about this one? All right, who's got another question? Yes, Allie.
Can we go over B on 53 on test 3 review?
Yes. Test 3 review. Sorry, which one did you say? Gosh, there's a lot of those. 53?
Yes, 53.
Nope. Is it this one right here, hopefully? 53B. Consider the following matrix. So part B says find a basis for the row space, right? Gotcha. So, I mean, I can sort of walk you through this one. I mean, in order to find a basis for the row space, I just take the matrix just exactly as it is, and I reduce row echelon form it, and whatever the non-zero rows are, I type those in as columns. And if you're okay with this, I'll just sort of I'll stop sharing this and just sort of write that general procedure down on my other thing. Does that sound like a plan? Let's do that. Okay, so to find row space, use reduced row echelon form, then a basis is non-zero rows of reduced row echelon form written as columns. Allie, does that make sense? You still have a question.
I understand the process. I was just not getting the right answer when I was doing the reduced row echelon form of it.
Gotcha. So what did you do the reduced row echelon form of this?
Yeah, and I got for rows, I got 1 0 1 0 1 negative 1 9th, and then a 0 row.
Can you do it one more time for me?
Yes, 1 0 1 0 1 negative 1 9th,
Uh-huh.
and then a 0 row.
That's weird. You got the first one right? I mean, you got part A right?
The basis for the column space.
I don't know. I'll look into it in the next minute and see if I can figure out what's going on. But I will say that if you understand the process, I think that's good. It could be that I don't know what it is. Let me check, and I'll send you an email in the next 5 minutes or so, hopefully. Either that WebAssign is wrong or something else is going on, and I'll let you know, okay? That's a good question. I think we got 9:19. So unless somebody has a question, that's like 20 seconds. Yes, Allie.
Can you post the recordings for both classes so if they go over different problems?
100% will, yeah. I will, what I'll do is, as I have been doing, I will take the recording, I will put it on our YouTube channel or whatever, and I'll also post links in Moodle. But yes, I'll do both, totally. All right, it is 9:20. Any other questions?
Thank you.
You guys are welcome. Thank you guys for being patient with me and understanding about me not wanting to be in Olin with a lot of people. Have a great wellness day. I'll see you guys on Tuesday. I've had a lot of questions about office hours. So I do have office hours today from 1 to 2, tomorrow from 1 to 2, Monday from 1 to 2. So I hope that you will come by. I also wanted to say that I have been getting emails like, gosh, I know you're busy, Dr. Spivey, but you should always ask. So I am busy, but you should never feel bad about asking for help or whatever. So I am busy, but I'm still not busy enough to help you do stuff. So Have a great day. Have a great weekend. I will see you guys on whenever, perhaps during office hours.
Thank you.
Thank you.